Hello, everyone, and welcome to the Singularity Lab, your home for breaking stories in science, technology, and futurism. Great to see you all today. Thank you for joining me for an early show. For some of you who are in the UK, this is perfect. For others of you, you may not know, we go live a little early sometimes, so I appreciate you guys being here. How's it going, Zero? Cool. John Brusso, great to see you. Lou, what's going on? Zero, cool. Great to see everybody here. Thank you so much for joining today, Laura. Amazing to have you. We've got an amazing guest for you today. We've got Dr. Mike McCulloch, who is a PhD and author of Physics from the Edge. His theories about inertia, alternative propulsion, and faster than light travel are pushing the boundaries of known physics. He has proposed a new cosmological model for inertia called Quantized Inertia, which predicts galaxy rotation without dark matter. I'm super excited. Ladies and gentlemen, without further ado, Mike McCulloch. Mike, how are you today?
Hello, I'm fine, thanks.
Fantastic. Well, it's great to have you. I really appreciate you being here. So today what we're going to do, and so just I'll give folks a little preempt of what we're going to get started with. So you've got a presentation. If you want to go ahead and start sharing your screen, and then I'll get that up on the screen. We're going to go through the presentation. As you guys in the Chatterverse have questions, feel free to pop them in. And at the end of the presentation, we're going to do a Q&A with Dr. McCulloch. All right. So let's see. I think I've got you here.
Now.
There we go. All right, we're ready to rock. It's all you, sir.
Great, thanks very much. Thanks for inviting me. So I'll be talking obviously about quantized inertia. I'm from Plymouth. I'll first of all talk about inertia itself, what quantized inertia is. I'll show you some astronomical evidence, some tests for thrusts in the lab that we've been doing, and some applications, view thrust and energy. Okay, just as a quick skip from my background, I got a BSc in physics from York, PhD in ocean physics. I was a scientist at the Met Office for a while. I'm now a lecturer in geomatics, which is a maths of positioning in space. And since 2018, I've been a research-only lecturer at Plymouth, funded by DARPA. And I've published 25 papers proposing this theory and a book called Physics from the Edge, which is shown on the right. Okay, so the main problem that started me off was galaxy rotation. So this is obviously a galaxy. This is the Andromeda galaxy. And if you look at the stars in it, so you can see this yellow star here orbiting around, then it'll feel a certain amount of gravity from the matter we see, which I've shown with this white arrow here. But also, because things tend to continue in a straight line, what we know is the inertial law, it'll see a force outwards called the centrifugal sometimes, or the inertial force. And it was found that this centrifugal or inertial force was many times bigger than the gravitational force. So astronomers added dark matter to the galaxies to boost the gravitational force and to balance the whole thing, because otherwise the galaxies should simply be flying apart.
Right.
But I don't like dark matter because it's very arbitrary and it has to be adjusted for every galaxy.
So is dark matter, quickly, is dark matter something that is purely theoretical, and have we inferred it through experimentation, or is this simply mathematical?
It's been inferred from the behavior of galaxies in a manner I described, but it has never been seen in the lab, despite 40 years of looking at places like CERN.
Great.
Okay. So as an alternative, I started to look at the old mystery of inertial mass. So things keep going in a straight line unless you stop them. So like this ladder, when the lorry hits the car, the ladder keeps moving. We know that is inertia, but we've never known why it happens. It's not due to the Higgs field, which only explains the mass of the quarks and a very tiny proportion of the inertial mass. So I proposed this new model for inertia combining relativity and quantum mechanics. So it looks a bit like this. So this black ball here, this is an object and it's accelerating to the right. And then from quantum mechanics, with a little bit of relativity, Bill Urhuh from Canada predicted something that's now known as Urhuh radiation, that is seen only by accelerated objects. And I've tried to show this on this diagram with the red color. So accelerating objects see a thermal radiation background that we don't, that unaccelerating objects don't. So that's shown here. Also, relativity says that information from this black area behind the object will never catch up to it. So this produces a horizon, which is shown by this boundary here, and this comes from relativity. And the new bit of quantized inertia is that I'm assuming that this horizon damps the Urhuh radiation. So I've shown that with the blue color here. You can see that Urhuh radiation is very intense and hot in front of the object, but between the object and the horizon, it's sort of blue. It's much colder. There's less of it. So this is like the Casimir effect. Waves of the radiation have been damped by the horizon. But this provides a very nice mechanism for inertial mass, because the radiation hits the object from in front, pushing it back, but less hits from behind, pushing it forward. So it tends to push the object back. It goes down the Urhuh radiation gradient from red to blue. So I published this in a paper in 2013, shown here. Okay, so this is a nice, it fits inertia very well, by the way. It predicts inertial mass. But it turns out that there's an amendment to this at low accelerations. If an object has a low acceleration, so I've shown one here, very low acceleration, then the Rindler horizon moves back because it's moving very slowly, and so things close to it information from close to it can get to it. So the Rindler horizon moves back, and at some point it's as far away as the cosmic horizon, which I've shown here, which is the horizon at the edge of the universe that we can't see beyond. And now
what is the Rindler horizon?
The Rindler horizon is the horizon I talked about before.
Okay.
Yeah, that's a good point, because I didn't mention it was a Rindler horizon. It's this one, the acceleration dependent horizon. So that's the same one as this. So it's now moved back. So it's the same distance away as a cosmic horizon. So what this means is that where before there was an imbalance between radiation on both sides pushing the object back, now it's all symmetrical. So the radiation is pushing equally on the object, and so it should not have any inertial mass at all. The mechanism for inertia has disappeared completely. So it turns out you can model that with this formula here, which is very simple. So the modified inertial mass m prime is equal to the original one times this factor, which has, again, it's very simple. It's just got the speed of light squared divided by the acceleration of the object times the Hubble scale, the size of the cosmos. So I published this part of the theory in 2007. Okay.
And what would just for this part of the theory, what would you have a layman walk away with? What do we need to know moving from this slide?
So the thing we know is inertial mass does not exist for very low accelerations, which is a huge change to standard physics. But as I'll show you, it makes some predictions that are borne out.
Got it. Okay, great.
Okay, so the great thing is that galaxies, the acceleration is large in the center, but at the edge where the problem is, where the models don't predict them right, the acceleration is very low. And it turns out that quantized inertia reduces the inertial mass of stars at the edge, so they have less of this centrifugal force outwards, and it's balanced now exactly by the gravity of just what we can see in the galaxies. You don't need to add any dark matter. So I showed that first in 2012 in this paper here, and then in more detail in 2017. So this is data from Galaxies. So this shows data from 153 galaxy rotations. On the x-axis, there's the expected acceleration of the galaxy. On the y, there's the observed acceleration. So if Newton was correct, all the data, which is shown by the gray squares, should lie along the diagonal, the dotted line. But for very low accelerations, the observed acceleration is bigger than we expect, so it's above the line. And the theory predicts it exactly. So the theory is a dashed line, and it fits within the square boxes, which represents the error of the data.
Wow, and previous models were not accurate, right? With the expected acceleration?
There is another model called MOND, Modified Newtonian Dynamics, by Mordecai Milgrom, and that also fits. You can see the solid line here, but for that model you need an adjustable parameter. You need to put in a number to it, 1.2 times 10 to the minus 10, whereas what I'm suggesting predicts this number itself, so you don't need to put the number in. but with MON, they put the number in and they tweak it until they get it right.
Okay.
But I don't need to do that.
Right. It sounds disingenuous to be tweaking the number to get it right, no?
Well, that's what they do. So it's slightly better than dark matter because at least they're only tweaking one number instead of several thousand.
Right.
But
Okay.
it's still adjustment. So the theory predicts a very simple formula. So the velocity of the star is 2 times the power 4 is 2 times g gravitational constant times the visible mass of the galaxy times the speed of light squared divided by the cosmic scale. So there's nothing in here that I can fudge or fiddle with. All of these values are known or observed.
Right. And they predict the actual acceleration.
That's right. So it's only got one chance to work, and it does. It works perfectly.
Wow. Okay. And how is, not to jump ahead, but how are people reacting to this?
Well, at the moment, most astrophysicists are ignoring it.
They are.
Is my impression. And my recent papers have been, well, they haven't been allowed on the archive. At a certain point, they stopped allowing me to publish papers on the archive. So astrophysicists may not be even seeing my papers, which is a shame.
Yeah. Okay. Very. Huh.
Okay.
So do you think you're intentionally being boxed out here?
Well, I wouldn't say it's a global conspiracy or anything, but I mean, the archive banning my papers, even the papers I published in good journals, they don't allow them on the archive. That is definitely wrong. That should not happen.
Okay.
So somebody's doing that.
Right.
Okay. So just to prove that it really is quantized inertia and can't really be anything else, this is a plot showing a galaxy. In the center, the star's acceleration is large, so they see short Unruh waves, and I've shown those at the bottom with these tight waves here. As you go out to greater radii, the acceleration is reduced, so you get longer Unruh waves. And it turns out that at exactly the radius where these Unruh waves are the size of the cosmos, that is exactly the point where the galaxies start to misbehave.
Interesting. Okay.
So that is a smoking gun, really. It means it has to be Unruh radiation that's doing it, because nothing else fits.
A couple quick questions while we have on that. Sonic Gravity asks, does the existence of a Rindler horizon cause us to rethink our belief that the cosmic microwave background might not be the light of the Big Bang?
Yes. I don't accept the Big Bang model for reasons that I can't really cover in this talk, but I have an alternative view of it, of the redshift. I think the redshift is representing the inverse age of stars instead, because in the past the universe was smaller, so fewer Unruh waves were allowed, so the physics was different. So I don't need to have a Big Bang.
Wow. That's a big deal. I look forward to having you back on the show to discuss that. But let's move on with the presentation. Yeah.
Okay. So the great thing about this is that it seems to have astrophysical backing, empirical support. So if we understand inertia in this way, can we control inertial mass, which would be a great, would be very useful. So imagine you have a setup like as shown here. So we have a cavity here with highly accelerated objects. It could be light, it could be electrons or anything inside. So highly accelerated that it sees Unruh waves, which are shown by the red color. And imagine that they're short enough that they can be damped by a metal plate, interact with a metal plate. And you put a metal plate above this object. Now these Unruh waves will be damped near the metal plate. So this is acting like a horizon now. We're making a horizon. And this should drag the object up because it's moving down the Unruh radiation gradient. Lots of hot particles are banging into it from below, but there are fewer banging into it from above, so it's going to move upwards. So I discussed this kind of thing in this paper here. So this would be a propellantless thruster. Normally, to get something to move up, we have to fire hot chemicals downwards and by Newton's third law, the object moves up. This doesn't need that. It just needs a metal plate or another way of damping the field above it.
So can you help me understand what kind of force is causing this to move up without combustion propulsion?
It's very similar to the Casimir effect. So the force pushing the plates together in the Casimir effect, that's because the quantum vacuum is being damped between the plates but not outside them. So there's a force that pushes them together. The only difference here is that because this acceleration is so high, we're energizing the vacuum, making it more substantial, and then damping it on one side asymmetrically.
Okay.
So you can think of this as one of the plates of the Casimir effect, and this metal plate is the other one, and they're just moving together.
Got it. Okay.
Okay.
And is this what? How would this be testable?
Well, I'm just going to go through that.
Okay. Sorry.
I'll tell you in a minute. So yeah, DARPA contacted me and I applied for funding and I was awarded $1.3 million. So my project aims to demonstrate, so this is what you're asking, demonstrate scalable quantized inertia thrust in the lab. So by scalable, I mean thrust that is definitely due to quantized inertia, but can be enhanced. We know how to make it larger and usable. Okay, so one way to do this, to answer your question, would be to have a laser, which is shown here on the right, laser light being fed into a fiber optic loop, shown here, and the photons go around the loop, they accelerate very fast, Unruh waves form, you put a metal plate below it, and that should push the fiber loop down, which can be measured. So according to the theory, the force that we should get is proportional to the power you put in from the laser. The Q factor of the loop, so that's the number of times the photons go around the loop without being dissipated as heat. The radius of the loop divided by the speed of light times the distance from the loop to the metal plate at its closest point. So we've been doing that. I have a lab in Madrid, Spain, organized by Professor Jose Luis Perez Diaz, and with also Dr. Javier Curella. And the important piece of data is this second row here. This is from a paper we're trying to have published. So the power we're putting in is 0.129 watts. Radius of the loop is about 15 centimeters. The predicted thrust is about 6 micronewtons, so it's quite a small thrust. And what they saw in Spain was 10 plus or minus 6 micronewtons, which is consistent with the with 6. You can see when they had half the power, they were getting getting about half the thrust, but it wasn't significant. It wasn't different from zero in that case.
Wait, it wasn't different from zero in that case? What do you mean?
Yes, so the first one with the less power, the observed thrust was 3.9 plus or minus 6, so it could well have been zero.
Oh, I see.
But we're excited about this second test because it was 10 plus or minus 6, so it was definitely above zero.
Right. That's incredible. Okay.
So that's good news, but we need to replicate it, of course.
Right. And how long ago was this done?
Oh, this was about 18 months ago now, something like that.
Okay. And then you're trying to replicate it currently?
Yes. So we're trying to do it again in Spain with more controls. And also we're setting up a lab at Plymouth to try and reproduce this same test. And we're trying to eliminate all possible artifacts, which is the big trick.
Right.
In this sort of work.
Okay. Just because you're dealing with such tiny energy units?
Yes, that's right. The other way we're trying to go is to enhance the force. So we don't need such sensitivity. That would be good. So I'll talk about that later as well.
Okay. Can I ask you the metal, the plates and the metal? What sort of metals are the plates made from?
They were aluminium in this case.
Okay.
So the great thing here is that the observed force to power ratio is 0.08 newtons per kilowatt. So for every kilowatt you put in, you would get this number of newtons out. and this is better than the ion drives that they use in satellites at the moment. And it's better than them without the need for fuel. So you wouldn't need fuel. You just put a solar panel on your satellite, and that would do it.
Wow. Which is fuel. I mean, you're talking about
propellant.
Having to carry fuel. I understand.
That's right. Yes, I should really say propellant.
Right.
Instead of fuel.
Got it. Fascinating.
Okay.
That's amazing. Okay.
So ways to enhance this thrust. So I've been trying to think of ways to enhance this. One way to do it would be to use, instead of normal glass and fiber optic, to use fluoride glass, which has up to 100 times the transmission. So we could have far more coils of it. And the thrust depends on Q, which is the number of loops you have. So with 100 times the transmission, we could get 100 times the force, which would be about 8 newtons per kilowatt. But this would be quite bulky because we'd have a lot of loops. It would be quite heavy. So it would be better to make only one loop and then tune the laser light so that it fits exactly inside the loop. So this is a bit tricky to explain, but I can explain it using St. Paul's Cathedral, perhaps, because there they have what they call a whispering gallery. So an elevated part of the cathedral, they have this gallery, and if you stand there and speak, then the sound from your voice will go around the gallery, come back to you, and the wavelengths will be such. It will select certain wavelengths that constructively interfere when they come back and meet each other again. So it will keep going around, constructively interfering with itself, so it won't be damped as much as you would expect. So what I'd like to do is do a similar thing with light. And some things exist called whispering gallery resonators that do this kind of thing. And then you could put laser light into a loop, and the Q factor could be on the order of 1 million or more.
And light can operate on the same principle as sound in this okay.
That's right. This has been done on a very small scale. They have these laser optical resonators. So I'd like to use one. Is what I'm saying. So I think using this method we could improve the 0.08 newtons per kilowatt to something like 8 newtons per kilowatt.
Right, to maximize the efficiency. Wow. Yeah. Okay.
So that would be very good. So that's a way to do it using light, but there are other alternatives to doing it, different pathways. So a guy called Frank Becker contacted me in 2017. He'd read my papers, and he thought an experiment that he had done trying to reproduce a T.T. Brown effect could be evidence for quantized inertia. So we designed an experiment, and he received help and experimental help from Ankur Bhatt, who's actually an actor, but also a qualified electrical engineer or mechanical engineer, one of the two. Sorry, electrical engineer. And they experimented, and they published their results here. So this pathway, well, the explanation is as follows. So normally you have an accelerated electron, which is shown in the top panel, accelerating to the right. In quantized inertia, it sees more under waves in front and behind, so it gets pushed back, goes from red to blue down the gradient. But if you have capacitor plates, which is what Becker and Bhatt are doing, then when the electron accelerates, the capacitor plates damp all the underwaves in front of it. But obviously there are some underwaves outside still, so it gets pushed forwards. And then when the electron bangs into the anode here, it pushes the capacitor. So it gets an extra kick or a thrust. And quantized inertia actually predicts a force shown by this equation here. So the force is a constant times the current you put in times the area of the plates divided by their separation squared. And this is a plot of the results of Becker and Bhatt, showing the separation of the plates, capacitor plates on the x-axis, and the force they got on the y-axis. And the black diamonds show the observations, and the squares show the prediction of quantized inertia. And I should make it clear that there's nothing adjustable, again, in this formula. it's a very simple formula. There are no adjustable parameters, but it fits very well.
Right.
And since then, very recently, a guy called Richard Mansell, a company called Ivo Limited, has reproduced these thrusts, these observed thrusts. So we have two examples now. But the very exciting thing is that at very small separations, you can see this is a separation of about 10 micron. The thrust you get is about 100 newtons per kilowatt, which is much bigger than the 0.08 we had before. So if we can confirm this, that would be this would be a good pathway to use.
Got it. And I'm sure you're about to go into how we can what tests we can do to confirm this or to test this.
We need more people to try it. Richard Mansell is the second. We need more people to do it, to verify what's going on, and especially university labs will be very welcome because they have all the equipment. So if you want to see how this equation here is derived, you can see my paper, which I've published on ResearchGate, because I can't publish it on the archive. It's this one here, thrust from symmetric capacitors using quantized inertia. Okay. And there's another very recent experiment that I'm quite excited about by Moddel et al., which was published in Physics Review Research here. So what he had was two palladium plates with an insulator between them, and he had electrons tunneling across the gap at a very high acceleration. So they would see Unruh waves, which I've shown with the red here, but then they put a Casimir cavity above it with a transparent dielectric and a mirror, and I would expect this to damp the Unruh waves. So I've shown this with the blue color here. You can see this kind of blue trough here where there's no Unruh radiation, and you would expect then electrons to start moving from the red to the blue down the gradient. And in fact, they did see a current between these two palladium plates, and the mass flux was about 10 to the minus 9 kilograms per second, and QI predicts a similar value. So this is also very interesting.
And can you give us a little context as to what sort of experiment this was, how this was derived?
This is, so Gallup Moddel was working on photoinjectors, which are, what happens is light comes in, excites the metal, and then you get electrons moving about. What they had not expected was when they, normally you have a potential difference between the upper and lower palladium plate. What they didn't expect was that when the potential difference was apparently zero, they were still getting a current between the two plates. So they wondered what that was due to, and it could well be due to quantized inertia.
Got it. Okay. Okay.
So I'll now talk about a few applications. So the obvious one is satellite drives or launching things. So what you could have is some kind of device here with a battery. So the best batteries that are being planned at the moment are lithium air batteries, which give you 1.8 kilowatts per kilogram of mass. And then above it, you could put a horizon drive, what I call a horizon drive. So it could be the loop, it could be the capacitor, or it could be the Moddel Photoinjector kind. So the total weight is 2 kilograms, 20 newtons down roughly. A horizon drive might give you 10 to 100 newtons per kilowatt. We've got 1.8 kilowatts from the battery, so we should get a force of somewhere between 18 and 180 newtons up. So we're getting close to levitating and launching things with this sort of technology.
Wow. Okay. You're getting to the point where you actually have enough energy that could create a launch.
Yes, that's right.
Real quick, I'm sorry to interrupt. A quick question here. I think this was from our last slide. How does the electron experience the drag inside the capacitor? Doesn't the Casimir effect require the absence of external matter participating in the vacuum?
Was that referring to this slide here?
I'm not positive. I think. How does the electron experience the drag inside the capacitor? I think so. Doesn't the Casimir effect require the absence of external matter participating in the vacuum?
So the Casimir effect would push these two plates together because outside there is some radiation, but inside there's none. You can see it's black inside. So yes, they'll be pushed together.
Got it. Great.
We're talking about an electron inside the capacitor plates now. So it's a different thing.
Perfect. Got it.
Okay, so another way to apply this might be to develop nanocavities. I like to call these floating bricks. So I've recently shown mathematically, so the paper's at the bottom here, that if you build one of these horizon drives small enough, it'll work with no input power at all. So it would have to be about 0.1 micron. So you'd have to be using nanocavities, but it might look something like this, where you've got little shapes that would damp the quantum vacuum more above than below. Some people may recognize this as looking very much like the M drive, but on a very small scale. So if you look at one of these, you might see an Urhuh field that looks something like this, with blue above and red below, which would be pushing the material up. And I calculated if you make them this small, that they should self-thrust, they should self-levitate. So you could build a material, you could make a material that just sits there above the desk, which sounds crazy, but mathematically it works. I don't know physically whether it would. But
where would the disconnect be there if theoretically it works, but you're not sure if it would work in physical reality? Is it where would you identify the disconnect?
Well, it's tricky because I've modeled. I haven't considered certain things such as thermal fluctuations in the metal, other electromagnetic fields that might mess things up. I've just simply assumed that Urhuh waves can be damped by this metal perfectly, whereas in fact that may not be the case.
That makes perfect sense. Got it. Okay.
Maybe only damps 1% of them or something. We just don't know that.
Right, because there's so many variables. It's very difficult to incorporate all of the variables into your mathematics. Is that accurate?
That's right. I'd have to use an advanced model to do it properly. I just used algebra in this paper.
Right, not a quantum computer.
No. But that would be nice. It would be nice to make materials that thrust by themselves.
Yeah, that's incredible. That's theoretically incredible. Yeah.
Yes, and this is a slide from Star Wars Rogue One, just to illustrate the point that you could make things just float. Okay. So another application would be a smoother ride. So this is getting a bit into other possibilities like the Nimitz UFOs and Tic Tacs and that sort of thing. So if you have a normal reaction engine, which is shown above here, and you have a rocket with a flower, a delicate flower inside it, and you fire the engine, then the flower will smash on the floor because of the recoil. The fact that it has inertial mass and it just wants to stay in the same place. And in quantized inertia, this is because as you accelerate the rocket up, a horizon forms here which damps the Urhuh field and pulls the flower down. So in quantized inertia, in that way of thinking, that's what happens. But a horizon drive will not do that. It will not smash the flower because it's using the mechanism of inertia itself. So in a horizon drive, you stick a horizon in front of the rocket like that. It damps the Urhuh field, the blue area here, and that pulls on everything equally. So the rocket goes to the left, the flower goes to the left with the same acceleration. So you don't get the flower doesn't smash, and you don't get whiplash.
Wow, that's fascinating. Okay, and this is going to be the key. I mean, if we're ever going to create, FTL or warp or any sort of anti-gravity machine, then we would have to be able to ensure that we don't squish the flower.
Yes.
Fascinating. Okay.
Yeah.
Great.
Okay. We could also, from this method, get new kinds of energy. So I published a paper here, energy from S-shaped rotors. So what I'm trying to say is that you could have a shape which has an axle, and it's an S shape. And so if it's accelerating fast enough, or if it's small enough to work off the quantum vacuum, then there will be fewer Unruh waves inside, so I've shown it blue, than outside, so it's red. So that means you'll get a force on these loops pushing inwards, and it would rotate. Oops.
Can you remind me what the Unruh field is?
So whenever something accelerates, it sees a uniform field called the Unruh field, which has now been observed at CERN. Any accelerating object sees Unruh radiation, what's called Unruh radiation.
And how is it? I guess I'm just trying to understand why it's a separate form of radiation. Like, what is the distinction?
It's because if you have an object that's accelerating, it will see this radiation, but if you have another object next to it that's not accelerating, you won't see the radiation at all.
I see. And so this is the idea of this being quantized radiation, is that it's a part of the fabric of the universe as opposed to something that is causing drag, in layman's terms. I mean, is that?
Yes, it's part of the fabric. It's like a quantum vacuum, but it's a more energized, more energetic version of the quantum vacuum. What it's saying is that when you accelerate, the quantum vacuum becomes more energetic. Right.
Okay. That makes more sense. I'm trying, Dr. Mike. I'm trying here. This is complicated stuff.
You're doing great. Yes. So because there's less Unruh radiation on this side pushing that way against the inner side of the curve, and there's more Unruh radiation outside pushing the other way, this will rotate, and you can use it to generate power.
Wow. Okay. Interesting. Wow.
So,
okay.
Yeah. So this would be a way to get energy from the quantum vacuum.
Cool.
I published it in a paper here in 2015, but I didn't actually use an S. At that time, I used a double S, which is actually I don't mean anything political by this, but it was a swastika. So you see, if you put another S there, you get a swastika. So I actually called it energy from swastika-shaped rotors, but S is a lot better and less politically problematic.
Yeah.
I should have thought of the S first, but I'm sorry, I didn't. Anyway, okay, and then there's also LENR, or cold fusion. So I've tried to explain that using quantized inertia as well. So this is the electrolysis of heavy water with palladium and platinum, and they found an excess heat emitted in the palladium, and it seems to occur when you have very small nano cracks in it. So my illustration is on the right of what I think is happening. You have two deuterium atoms, and they're accelerating very rapidly in the crack, so they see Unruh radiation again, this red stuff, but between them there's a sheltered area, as there would be for the Casimir effect, and this pulls them together and enables them to overcome their Coulomb repulsion if the crack is less than 28 nanometers in size. So I published a paper on that one as well.
Interesting. Okay.
Okay. And then there's interstellar travel. So because this kind of propulsion would be propellantless, the problem with getting to Proxima Centauri b, which is shown top right here, in a human lifetime, is we have to carry so much fuel to get close to the speed of light that it makes the rocket too heavy to go there in the first place. So it's impossible. But with the horizon drive, so I've shown that here with the ship that damps the Unruh field in front of it, it would be possible. And we could use a fission reactor that I've shown here, horizon drive. I've done the calculations, relativistic calculations, and it turns out that you could get to Proxima Centauri in about just over 12 years.
Wow. And how far is how far is Proxima Centauri?
That's 4.3 light years.
Okay.
Um,
Wow, it's fascinating. Okay. And the QI Horizon drive, that's the second. Okay, so you've got, what's a safe 400 fission reactor?
that was a reactor built by some guys at NASA, almost in their spare time, and it was half a ton, and it produced 100 kilowatts. And this was told to me by a guy called Travis Taylor. He told me about this reactor.
Got it. And so that's 512 kilograms, whereas the Horizon drive is 5 kilograms.
Yes.
Got it. Wow. Okay.
So you might design a spacecraft like this. This is a spacecraft designed for Horizon 1. So you'd have, perhaps you could use a capacitor, or you could use a laser loop in the center, and then you'd have a rotatable Urhuh shield. So this gray area here would damp the Urhuh radiation in front, so it would pull the whole thing forward. And then when you wanted to slow down, you could rotate it to behind the loop and slow it down that way. And it would need a shield, of course. And that's the reactor, the red rectangle, and an antenna to phone home.
Amazing. Quick question from Sonic Gravity. Is it possible, if the Higgs field was a quantum field tying mass to our instant of Planck time, the observation of Urhuh radiation might actually be tension in the Higgs from inertial time dilation?
Well, I'm not quite sure what he means, but it's quite clear that the Higgs field does not predict inertial mass. It's only about 1,000th of what we need at the moment, unless he has an alternative suggestion, of course.
I'm sure he does. I'm certain he does. All right. I'm sorry to stop you. I just want to make sure, because sometimes when we get these super chats, if I don't show them, then they'll disappear. So I want to make sure we got to them. So I appreciate you taking those for me.
Okay, sure. Yeah, so that's a potential design. And then, so just to list the applications, quite immediately we could, the first thing to do would be to have satellite, replace satellite propulsion. So we could use it for that. Satellites would be lighted to launch. Obviously, flying cars, new kinds of aircraft, structures that hover, launch, inertial dampening, no whiplash.
Right.
Energy from the vacuum. Interplanetary trips become a lot cheaper and easier. So, for example, with the Horizon drive, you could get to 100 AU in 2 months, and interstellar trips would be possible for the first time. Okay, so just to summarize, so quantized inertia explains inertial mass for the first time. It gets rid of dark matter. It has very good astronomical evidence. I published 25 papers to back it with evidence. It predicts a Horizon drive or an electric rocket. Our experiments are homing in on a pathway, well, probably about three or four, and we're setting up a testing lab at Plymouth to do this. And
you're doing this still under contract with DARPA. You're using those funds to set up the Plymouth experimental lab.
Yes, that's right. Yes.
Fantastic.
And those are the applications. And yeah, thanks for listening.
Yeah, that's fantastic. John Brusso had a question. Is that 30 to 40% speed of light? What do your peers say about that?
Oh, the main comments have been that at that speed, we're going to need a lot of shielding. It's actually, the speed would be 0.5 the speed of light in the calculation I had here. So particles will be hitting the ship at half the speed of light. So we would need a decent amount of shielding.
And what sort of shielding? What sort of shielding would you use?
There are several things that could be used. Metal shielding, even water would do. Anything that's very dense would do it.
In regard to the previous question, Sonic Gravity said, I'm just envisioning a bunch of, so this was his question in reference to the Higgs field. He says, I'm just envisioning a bunch of Higgs strings getting tightened when something accelerates and people calling that Urhuh radiation. So he's trying to explain Urhuh radiation with a tension in the Higgs string.
Okay. Well, if he can do that, then he should, yeah, he should write a paper on it. That would be helpful.
Let's see. Oh, here's a great question. And maybe we should have you back sometime to chat with Sonic Gravity, because he's got a lot of ideas. All right, Carrie says, how can one lower this? Oh, this is a great question. How can one lower the speed once we arrive? So we're traveling at 30-40% of the speed of light. We got to slow down. How do we do it?
Yes, well, I explained that here. So you accelerate at 1.3 meters per second for 3.7 years till you get to half the speed of light. Then you cruise for about a light year. Sorry, distance traveled then is a light year. Then you travel for 2.3 light years at that speed, which is 4.6 years. This is taking account of all the relativistic dilations. And then you would decelerate for 3.7 years. And if I show the next slide, the way you decelerate, instead of having this Urhuh shield in front, you rotate it to the back. So it then acts as a brake, because it pulls the opposite way then.
Ah, I see. Okay, this is starting to come together for me. Okay. Let's see. We've got about, I know you're on a pretty tight time schedule. We've only got you till about 4, which is about 13 minutes. So if you guys have questions specifically that you want to ask the doctor, feel free to ask those now. Aaron says, sonic gravity slowing down is just accelerating the other direction 50% of the time. Gloria says, rockets can't propulse through a 10-torr vacuum. Space travel is a hoax predicated on incredulous presumptions. Wow. What do you say to that?
Well, yes, I would respectfully disagree. I think it's quite clear that rockets have gone into space, and they do work.
They certainly do. They certainly do. What are your thoughts on, I know you mentioned the Tic Tac earlier. What are your thoughts on what we're seeing, what David Fravor and Dietrich saw? What are your thoughts on that?
Yeah, well, that's the first UFO observation I've seen, which looks really very interesting. I was thinking it could be several things. It could be a natural phenomenon that we just don't know about. It could be a UFO, of course, something from elsewhere. It could also be a government psyop of some kind, something to possibly disturb the population, like several other things that are happening. Or it could be people in certain departments looking for funding. So there are several things it could be, but it's the first observation of a UFO that I've been seriously looking at.
Yeah, that's definitely the thing that turned me onto this subject again. Casper says, I did not see the start of this, but what power source is used to power the craft?
Oh, the safe reactor, the fission reactor. Yeah, so I didn't bring that out enough, but this red block here, that's the Safe 400 reactor. And that's described in paper by Poston et al.
Millisecond said, can any of your theories explain UAP observables? Is it possible apparently very fast moving crafts have a different rate of time than observers may explain acceleration and sudden sharp angles?
Yes, well, quantized inertia, I mean, one of the reasons I'm interested in these Nimitz UFOs is because if quantized inertia manages to work in this way, then it would look like that, because you would be able to have almost instantaneous accelerations, because you wouldn't have the whiplash phenomenon.
How might you consider controlling such a craft?
Well, in a similar way to this interstellar craft, you'd have a highly accelerated core, like this orange loop. Then you'd have a movable Urhuh shield, which you can move around to different places. So whichever direction it is, the craft will go in that direction.
And then the sixth pool says, with time dilation, what would be the crew's perceived travel time to Alpha Centauri?
Yes. So I calculated that exactly. So from the point of view of the Earth, it would be 12.3 years, and from the ship, from the crew's point of view, it would be 11.7 years.
Oh, that's not too bad.
Yeah. Not too much difference at half the speed of light. But of course, this is a probe. It's not a manned. I haven't calculated it for a manned craft yet.
Fascinating. Are you familiar with Dr. Avi Loeb and his work with the Galileo project?
Oh, I've heard of the Breakthrough Starshot program, which he's involved with, I think.
Yeah, Starshot's interesting as well. Yeah.
Yes, that's an interesting one. That's another way to do it with very, very tiny nano probes.
Sonic Gravity wants to know, do we see QI at the edges of our solar system too? Why or why not?
Yes, that's a very good question. And the answer is possibly that a lot of the very distant objects that have been seen are behaving anomalously, leading people to suggest that there is a Planet 9 out there. But another way to, and I haven't modeled it yet, but another way potentially to explain that is to say that their inertial mass is slightly less than we expect because of quantized inertia.
Right. Okay. What do you think? Like, what are your? I know you're building the lab in Plymouth, and your next experiment is going to be to replicate the experiment that you showed, and I think it was maybe slide 5 or 6 or 4 or 5. Is that what you're working on next?
Yes. So this one.
Yes.
So we're going to reproduce this and use a very finely designed torsion balance to measure the thrust and try to enhance the thrust at the same time.
And based on based on the progress you're seeing, if you can replicate this, where do we go after that? And like, let's say, for example, we are actually like, let's say for a moment that this quantized inertia was the key to accomplishing long-term space flight. How far from where we are today to actually producing something that can do that? How many years? How much time do you think we are from that?
So perhaps launching something, if all goes to plan, we should be able to do it by the end of the decade. I would like to do that.
Wow, that's fast.
Yes, because the technology already exists. If we can just demonstrate that the theory really is producing these thrusts, then the technology already exists to enhance the thrusts enough to produce launch.
Right.
So we just need one incontrovertible demonstration. That's all.
Right. And so you're finding the biggest challenge that you're finding is, since you're not able to publish in the archives, you're having difficulty finding people to reproduce your experiments. Is that the challenge? Is DARPA not able to help get this information out there and get access, or is that they give you the money and they say you do it?
Well, they've already helped an awful lot by giving me funding, which helped an awful lot with persuading other people to join in.
Right. It gives you credibility to be able to attract more people.
Yes, that's right. And several labs around the world have joined in. So as we speak, there are something like 6 or 7 labs that are liaising with me to try and do experiments of various different kinds.
Right.
So it's moving quite rapidly, and they're driven, of course, because they want to patent things and develop products. So right. I think my job will be over when I produce this demonstration. Then
They'll be like, thanks, Doc.
I'm hoping the industry will take it from there. And
yeah, and so you mentioned quite a few of the applications earlier. Obviously, long-term space travel is one. You mentioned satellites. What were some of the other applications that you mentioned? Definitely the Star Wars warship. I'm down with that. Okay, yeah. What do you mean by satellite station keeping?
At the moment, satellites use various kinds of rocket or ion drive to keep them aloft, but they run out of fuel in a few years, so they fall down. With this method, with quantized inertia,
I didn't even know that. I thought satellites go into orbit and they don't need fuel. They just orbit. That's not accurate.
No, because they feel friction with the atmosphere, so eventually they slow down and they fall.
So is it lower Earth orbits that require more power, and then higher Earth orbits require less power?
Yes, that's right. Yes, because there's more friction, of course, at LEO. But if you could put a horizon drive on them with a solar panel, that would keep going for
indefinitely.
Well, yes, that's right. So that would be good.
Right, that would be good. Let's see. Sonic Gravity asks, "What are the units for the variable d?" I don't know which slide he was reacting to. Aaron says distance to the metal plate. Is that right?
That's meters. Yeah, it's a distance in meters. So, if that's the one he means.
Got it. So other applications would be flying cars and hoverboards, yes?
Yes, that's right. Yeah, hoverboards. I didn't mention those, but structures that hover, I guess that would cover it.
Yeah, that would be fascinating. I mean, that's kind of that's private industry's wet dream right there. They'd make some huge money. Sonic Gravity says, so gamma is the gradient of the vacuum?
Gamma. I'm not sure which slide he's referring to there.
Yeah, Sonic, if you could, or the drag. I'm not sure which he's referring to.
Is he referring to this slide? So pi times the power times the quality factor times the radius divided by speed of light, and the distance.
Perhaps we'll have to wait and see what he says. As we kind of wind up here. Oh no, he said never mind. It's an R. He had mistaken. Okay, it's the radius. Got it. Okay, great. All right, fantastic. So, any other final thoughts that you'd like to leave us with along this? And yeah, I'm curious, like what anything else that is fascinating you or interests you, or that you're getting excited about as you leave us today.
Well, I guess I could ask if anybody knows of any kind of high-powered fiber optics, or can see a way to confine a laser into a loop, then please get in touch, because I'd like to know how to do it.
High-powered fiber optics that could send lasers through a loop. Is that what you're asking?
Yes, that's right. That's what I'm trying to do. That's the big challenge at the moment.
Interesting. All right. So you listeners out there, make sure you share this show. Make sure if you know somebody who could answer that question or help Dr. Mike McCulloch out here, share the show. We appreciate it. And
please spread the word as well.
Yeah, absolutely. Spread the word on this. We really appreciate you being here, Mike. I hope we'd love to have you back sometime. I know Brad from Sonic Gravity would love to pick your brain on some of his theories. He's a citizen scientist who's working on some pretty wild stuff. So he's always looking for somebody more in the mainstream to bounce ideas off. So we'd love to have you back sometime.
Okay, sure. Yes.
All right. I'll set that up with you and Brad. We'll do it another day. And again, thank you so much for joining us today. You guys have been fantastic, amazing questions here in the Chatterverse. And we'll talk to you very soon, Dr. Mike McCulloch. Thank you very much for joining us today.
Thank you very much.
Bye-bye.
Bye.